Hey guys, Buildzoid here, and today we're going to be taking a look at how DDR gets its DDR-ness. In other words, how double data rate is possible, because I'm sure you've heard that double data rate just means you transfer data on the clock edge, but like, how do you put any data on a clock edge? There's not exactly a lot of space on a clock edge for data. So that's what we're going to be taking a look at today. And we're going to be taking a look at a write burst operation and a read burst operation for DDR4. And we're just going to be using these two timing diagrams because they cover basically everything you need to know. Anyway, let's get into it. We're going to start with the write burst operation because this makes way more sense than a read burst operation when you look at them, like, depending on which one you look at first. Like, a read burst operation doesn't make sense until you've seen a write, in my opinion. So, anyway, let's get into it. So, the timing diagram here, we've got a clock signal. The clock signal is differential, which just means there's a positive and a negative version of it. There's a bunch of electrical engineering reasons for why you'd want a differential clock signal, but for the purposes of this video, we do not care. And you can tell, like, you can see from the diagram that it's a differential signal because you have, like, these two waveforms going on. So yeah, that's how we know it's differential. And a full clock cycle is from T0 to T1. So that right there is a clock cycle. And obviously in that clock cycle, you have these two edges. And then you have your next two edges from T1 to T2 and that kind of thing. Anyway, so that's the clock signal. And this is measured in hertz. So like if you're going to say, if you're going to talk about the memory clock, you can use hertz for that. Actually, you should use hertz for that because it's literally a clock. That's the whole point of hertz, is to measure frequencies. So if you say, like, if you have like a DDR4 3200 kit, it will have a 1600 megahertz clock, as in this signal right here is 1600 megahertz. You could take an oscilloscope, admittedly a pretty expensive one, and go and measure this, and it would be 1600 megahertz. So that's physically there. Anyway, below that we have the command bus. This is what is used to tell the memory stick what to do, or more like, well, this is basically to tell the memory stick what you want to do. So yeah, so that's the command bus. Below that we have the bank group address. This is specific to DDR4 and DDR5, like, well, to some memory standards. Not all DDR has bank groups. All DDR has banks, but not all DDR has bank groups. But anyway, so this is just an extra address like bus that is used for DDR4, DDR5. I think some of the GDDR technologies. Basically where we want to, like, it's just used to tell the memory stick where we want to do whatever we want to do. Below that we have the address bus, which is just used to more like, you know, the second part of where we want to do stuff in the memory. We don't actually, like, for the purposes of this video, we don't care about the address buses at all. We do kind of care about the command, but the address bus doesn't matter whatsoever. Then we have the data queue strobe. This you can basically think of as a secondary clock signal that is only present if there is a data transfer actually occurring. And then below that we have the data queue, and I don't know why I'm so bad at using a mouse, because that is a terrible highlight right there. But yeah, we have the data queue. This is a single-ended connection going from the memory controller to the memory sticks, or, well, to the memory chips. Each memory chip will have anywhere from 4 to, well, depends on the memory chip, but for DDR4 and DDR5, it's going to have anywhere from 4 to 16 data queue connections. Each data queue is used for transferring 1 bit of data at a time, except, you know, you have 4, 8, or 16 of them, so they're in parallel. So, yeah, in this diagram, we only see one data, like all of the data queues are represented with the single data queue in the timing diagram, but basically whatever's going on in this data queue is happening simultaneously on all of the other data queues. So if you have a like X4 memory chip, it has 4 data queues, and they're all going to be outputting out data, like they're all going to be outputting data, same as like what we see in this diagram. Anyway, like basically, if you wanted to extend this diagram, depending on if your memory chip has X4, X8, X16, you would take this DQ portion of it and you would just copy paste it a bunch of times. There's no, there shouldn't be any timing mismatch between the data queues. If there is, that you have, something is wrong with your memory chip. Like, it shouldn't do that. So anyway, But from the data queue, you can see that over here we have like an actual data transfer going on. And when the data queue is idle, you can see that the data queue strobe is idle. Now, obviously, it's not idle. There's this little period of time called the write preamble. And this is basically to just make sure that the data queue strobe is actually going before we start transferring data. Because if you start transferring data and the data queue strobe isn't going, you're going to have serious problems. So that's why we have this like write preamble period, and you have the same thing in the read diagram, which we'll get to when we get around to that. So yeah, you can think of the data queue strobe as a secondary clock that's used specifically during data transfers, whereas the main clock signal is ever present from the moment the memory is initialized, because without the clock, the memory can't do anything. It's like used for all of your timings, it's used for commands, it's used for absolutely everything. If you don't have a clock, your memory is like turned off or in some weird idle state. So the clock must be present. The data queue strobe is specifically used for data transfers. Anyway, now let's take a look at how a data transfer actually occurs. So this is a write burst operation, so we're sending data from the CPU's memory, well, from a memory controller. It doesn't necessarily have to be on the CPU, but you'll have a memory controller and it's sending data to the memory chip. So our memory controller tells the memory chip that it wants to write. So we send a write command and the memory chip starts getting ready to receive the data now. Then after some delay, we start the write preamble, so the data queue strobe basically starts up. And then after some more delay, the memory controller starts sending data out of alignment with the clock. And this is the wacky part, because in order to actually have data on the clock edge, you need to change the voltage level on the data queue before the clock edge, right? So if I wanted to send a sequence of, say, 0, 1, 0, 1, 1, 1, and then like 2 zeros, what that would look like as a voltage level on the data queue, because the data queue is single-ended, right? So literally the data is represented on the data queue as just a voltage level. So when we're doing this write operation, the memory controller, like, because we want to send a 0, we drop the voltage on the data queue. Then we want to send a 1, we raise the voltage back up. Then we lower it again because we want to go to 0. Then we raise it back up. We're sending a bunch of 1s, so we just hold it high for a little bit, and I just screwed that up. So we just hold the voltage high for a little bit, and then we want to send 2 zeros, so you hold it low, and then you go back to the idle state. And you'll notice that these transition points in the data are not on the clock edge, right? They're way out of alignment. And the reason this is done is because memory chips are incredibly dumb. And the reason memory chips are incredibly dumb is because if you have a CPU, that CPU will have one memory controller, and so it's relatively okay to have a a complex and expensive memory controller. It is not okay to have complex and expensive memory chips, because your one CPU, like a consumer CPU, can easily have 64 memory chips hooked up to it. It's not particularly common, but you could have as many as 64 memory chips hooked up to that CPU. If you're talking about a server CPU, that CPU could have hundreds of memory chips hooked up to it. So if you had complex, expensive memory chips, that would not be good. Having a complex, expensive memory controller is a much better option, because you only need one memory controller for up to hundreds of memory chips. So the memory controller is basically sending the data, the memory controller is shifting the transition on the data bus relative to the clock signal. So that when the data arrives at the memory, so when the memory chip actually goes to record data, what it's doing is, after this write command, at this point in time, because we have a cast write latency of 9, so after 9 clock cycles, right, so we go from T0 to T9, at T9, the memory chip goes and it checks the voltage on the data queue, and it sees that the voltage on the data queue is low, and it records a 0. And then at T9.5, which is our second clock edge, it goes and takes a look at the data queue and sees that the voltage on the data queue is now high, and it records a 1. And then at T10, it checks the voltage on the data queue, sees that it's low, records a 0. T10.5, it records a 1 because the voltage is high. T11, it checks again, the voltage is high again, so it records another 1. T11.5 records another 1. T12, 0. T12.5, 0. And T13, it doesn't do anything because we've already sent 8 bits of data. And you're sending 8 bits of data on each data queue line at the same time. So the memory chip would have actually, like in a full data burst, in a full write burst, like an X8 memory chip will record 8 times 8 bits of data in 4 clock cycles, right? Because you just go from T9 to, kind of T13, but not really because the data transfer is finished at T12.5, right? This is the last time we're actually checking the voltage level on the data queue. And so that's how a write burst operation works, is basically the memory chip is just using the clock edge as a trigger for sampling the data queue, right? And that's how you get double data rate in a write burst operation, because in like T9 to T10, that's 1 clock cycle, but we've recorded 2 bits of data in that time, right? We've recorded both our 0 and our 1, because we're just using each clock edge to check what the voltage level on the data queue is. And the memory controller is doing the difficult task of making sure that, actually outputting the data with ahead of the actual clock edges. Because if you had this transition point on the clock edge and the memory chip went to sample, that transition point, it would, in a perfect world, it would measure a voltage level of halfway between a high and a low. And, that's neither a 1 nor a 0, and things would get very awkward. So the memory controller has to deal with the whole shifting the data relative to the clock in order for the memory chip to be able to actually just check what's on the data queue at the clock edge. Anyway, a read operation really makes you realize how the memory controller is doing all of the heavy lifting, because in a read operation, again, we have our clock signal, we have our command bus, we have our data queue strobe, and we have our data queue. And our data queue strobe again has to start up before we actually start sending any data. And in a read, and the read starts basically, we say we want to read, right? You give the memory chip a address that you want to read from, which again we don't care about, which is why I didn't mention this. Obviously, for a write operation, you have to tell the memory chip where it is that you want to write. But anyway, we tell the memory chip where we want to read from, and then after a delay of CAS latency at, if this is T0, this should really be T11 over here, but the diagram decided to replace T11 with TA2. But anyway, after some delay, it doesn't matter. If your CAS latency is different, it's just going to change when that happens. The memory chip, basically during this time period between our read command and the actual data starting to be output onto the data bus, during this time, the memory chip is basically getting the data ready. It's loading it into its output buffers. And then after that delay, the memory chip uses the clock edge to trigger the transition of the data, right? So let's say we want to send that same sequence of 0, 1. Oh no, I'm doing the fancy ones instead of the simple ones. 1, 0, 1, 1, 1, 0, 0. Right, so at TA2, the memory chip goes and lowers the voltage on the data bus, right? On the data queue. It lowers the voltage on the data queue. At TA2.5, it raises the voltage on the data queue because it wants to send a 1. At TA3, it lowers the voltage. At TA3.5, it raises the voltage again. Man, I really wish these were just proper numbers. They're screwing me over so badly. Anyway, then for the next couple edges, it actually holds the voltage level constant because we're sending a bunch of 1s, and then it lowers the output voltage level again, and eventually we go back to idle, right? And so what you'll notice with this is when the memory chip is actually sending data to the memory controller, that data is the transition in the voltage level on the data queue happens on the clock edge. So if you had a memory chip sending data to another memory chip, it would not work, right? Like if you were reading if a memory chip was reading, if one memory chip was trying to read from another memory chip, so we were for one memory chip, it would be a write operation. For the other memory chip, it's a read operation. It wouldn't work at all because the memory chip, when you're trying to write data to a memory chip, it samples on the clock edge. And when you're reading data from a memory chip, it transitions the data on the clock edge. So on a clock edge during a read operation, there's no data there, right? Like that's kind of the whole issue. Like this is a 0.5. And actually, in reality, it would be basically random. Sometimes your transition edge might be, a little bit faster or a little bit slower, and so sometimes you get a 1, sometimes you get a 0, and it's just like you'd get a random number generator in reality if you tried to read the data on TA2 or TA2.5. Like what's at TA2.5? Nothing. There's not valid data right there. So what the memory controller does during a read operation is that internally, and there might be other ways of doing this, but I'm aware of at least one style of DDR controller doing this, is that the memory controller internally has a second clock signal known as a read clock, which is 90 degrees shifted relative to the actual clock that the memory has. So basically, inside the memory controller, we have a clock that looks like this relative to the main clock, right? It's on a 90-degree shift, so it's out of alignment with the main clock by 90 degrees. And so the memory controller is using this this read clock that's at 90 degrees to the memory clock to actually sample the data that the memory is sending, because the memory is is transitioning the voltage level on the data queue on the actual clock edge. And so if you wanted to read the data, you need a second clock signal that's out of a line, 90 degrees out of phase, in order to actually hit the part of the data queue where there's data on it and not a voltage transition point. And theoretically you could also have a memory controller that just uses a fixed delay relative to the clock signal, but I would assume that's probably way more complicated to do than to just have a second clock, a read clock signal that's 90 degrees out of phase with the main clock signal that you have. Anyway, that's how double data rate is possible. You are literally so during a write operation, when you're sending data to the memory chip is sampling the voltage level on the data queue every single clock edge. And because the memory controller is very clever and fancy, it can shift the data relative to the clock so that you can actually get valid data when sampling on the clock edge. During a read operation, the memory chip is incredibly dumb, and so it changes the voltage on the clock, it changes the voltage level on the data queue on the clock edge, right? And this doesn't happen instantly. That's why you have why there's slopes in these timing diagrams. You'll also notice that there's a tolerance to those slopes over there, right? There's not just a thin line. There's a bit of tolerance because you just shouldn't be trying to measure anything at that point in time. But anyway, so the memory chip during a read operation is outputting, is transitioning the voltage level on the data queue on the clock edge, and the memory controller has its own secondary I would assume most memory controllers just use a secondary read clock. Has its own internal clock that's 90 degrees out of phase with the memory clock that's actually used to sample the data that's coming in from the memory chip. And this way you can, get, you can sample the data bus twice per clock cycle and get valid data by doing this. And that's how you get double data rate. Hopefully that makes sense, because, especially the read operation is just kind of wacky. Because, if you look at this timing diagram and you've never seen a write operation, then it's this just doesn't work if you're not aware of the internal functionings of the memory controller. Because for this, the memory controller is actually doing all of the heavy lifting. Same goes for a write operation, right? Because, Anyway, so hopefully you found this somewhat interesting. Potential, maybe useful. I don't know. But that's how double data rate is done. The memory controller does all of the heavy lifting. And the memory chip just the memory controller does all of the fancy data alignment stuff. And the memory chip's just there. Anyway, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, all the usual YouTuber merch. And then I also have a Bandcamp that you might want to check out. So, yeah, that's it for the video. Thanks for watching, and goodbye.